Last time, I told you that AI learning is just a ball rolling down a valley. Check the slope. Take a step downhill. That's gradient descent. But I deliberately kept one huge problem from you. Inside a neural network, there are trillions of knobs. And for every single one of them, we somehow need to know which way should it turn, and by how much. If you tried them one by one, the universe would end before you finished. The magic that solves all of it in an instant. That's today's star. Backpropagation. Welcome back to Minimal Lab. Let's break it down. A neural network is built from layers, stacked one after another. The input passes through layer 1, layer 2, and so on, until an answer comes out the other end. And that answer was wrong. We got a loss. Now here's the question that matters. How much is each knob responsible for this mistake? For knobs near the output, it's easy to point fingers. But what about a knob buried deep inside? Many layers from the end. Its tiny adjustment ripples through layer after layer before it ever touches the answer. Tracing that influence, knob by knob, it looks impossible. This is where physics and math come to the rescue. The key is called the chain rule. Picture a train of meshing gears. Turn the first gear just a little, and that rotation passes to the next gear, and the next. So how much does the very last gear move? You don't need to simulate anything. Just multiply the transmission ratios of every gear in the chain, and you have the answer. In physics, this is how sensitivity propagates. If temperature affects pressure and pressure affects volume, then the effect of temperature on volume is simply the product of those two effects. A chain of derivatives, that's all it is. And a neural network works exactly the same way. The influence of a deep knob on the final loss is the product of sensitivities, layer by layer, from that knob all the way to the output. And here is the genius part. The naive approach. For each of those trillions of knobs, you'd redo the whole chain of multiplications, all the way to the output, every single time. Trillions of knobs. The computation is astronomical. So we flip the direction. First, compute the error at the output. Then send that error backwards, from the output, towards the input. Each time it passes through a layer, we take the responsibility arriving from behind, multiply it by that layer's sensitivity, and hand it on, like a bucket brigade, passing the blame backwards, layer by layer. In physics terms, it's heat diffusing from the hot side to the cold side. Same structure. And with one single backward flow, every knob's responsibility is determined all at once. Brute force, the age of the universe. Backpropagation, an instant. That difference is what made modern AI possible. Now let's watch one full cycle of learning start to finish. 4 steps. Step 1, the forward pass. Feed the input through, get an answer. Step 2, the loss. Measure the gap between the answer and the truth. That's the height of the valley from last time. Step 3, the backward pass. Send the error backwards and get every knob's responsibility, the gradient. Step 4, the update. Nudge every knob one small step against its responsibility. That's the step downhill from last time. Then back to step 1, repeat millions of times. So here's how the two videos fit together. Last time, walk downhill was the strategy. Today, backpropagation is the calculation that delivers that step to every single knob. Only when the two mesh together can AI actually learn. But backpropagation has a weakness. Multiplying sensitivities across many layers means this. If those numbers are smaller than 1, the signal shrinks with every step. By the time it reaches the deepest layers, it's practically 0. This is the famous vanishing gradient problem. In physics, it's a signal decaying with distance. It simply doesn't reach that far. And if the numbers are bigger than 1, the opposite happens. The signal explodes. That's why modern AI relies on tricks like activation functions and normalization. They keep this flow well behaved. So much of deep learning engineering comes down to one thing: making sure the backward signal arrives cleanly all the way down. Let's put it all together. The problem: trillions of knobs, and we need each one's share of the blame. The key: the chain rule. Multiplying sensitivities like meshing gears. The trick: send the error backwards, from output to input. The result: one backward flow, and every gradient is known all at once. So when AI fixes its own mistakes, the reality is almost disappointing. It's just letting the error diffuse backwards. And with that, you now have both pillars of AI learning: gradient descent and backpropagation. Next time, the hardware hero behind all this math. Why AI needs GPUs, explained through the physics of parallel computing. If you want to keep understanding AI through physics, subscribe. And there's a free notebook in the description where you can trace backpropagation by hand, step by step. See you at the next layer.